In the previous video, we walked through one of the two t-tests that we encounter here in Chapter 11, and that was where we assumed that the population standard deviations were equal, that there was one underlying sigma that was true for both populations. We walked through this example with Abreu and Freeman, the two MVPs from 2020. You can go back to that video to hear more about what we were doing there, but in short, we had exit velocity. We want to know who's hitting the ball harder, and we're taking the sample to be each of their at-bats that ended in a in-play hit, or when they hit the ball into play. It doesn't have to be a hit, it could be an out, as the sample. And in the population then is really them as their all the times when they could hit the ball, not just the times that they batted this season. So we have a sample of varying sizes, 176 and 182. And so, we walked through the process of pooling that variance, taking the two S's each as a good estimate or an unbiased estimate for that underlying sigma. And so we smushed those together with a weighted average that gave us that pooled variance, this 178, and we used that to do the calculation here, specifically the pooled t-test. And we came up with a t-value of 0.297. And so we did not reject the null. We didn't have enough evidence to say either hitter, or that they're not the same, underlying power, their average power, their average exit velocity. We could not reject the null that those are the same. Okay, we also had to calculate degrees of freedom. We, with a t-value of under 0.3, we probably did not need to reference the t table, but it is important to calculate the degrees of freedom and actually find that. And what we're going to do now is turn and look at that other t-test. And so we'll come back to this 0.297 and this 356, but we'll see that these differ a little bit depending on, again, what t-test we use. So let's clean this up a little bit. We'll take a little bit of this info with us. And we'll clear that out. Okay, just so we can remember their values there. And let's talk about now. We're going to say that we don't think, sigma. I guess we can say sigma alpha and sigma f in our case. We're going to say that we can't make this statement. So we don't know. Maybe it is, maybe it's not, but we don't know this for sure. Okay, and so because of that, we're going to still be in the t, right? We're still working on that. We don't know what these are, and we're also saying that we don't know that they're the same. So that leads us to the t test still, but a slightly different version. And this version is going to feel more familiar, especially considering chapter, where are we coming from? Chapter 10. And this version is t. Again, the top is that difference between the two. Okay, I'm gonna try to stick to the a and f, and so here we have our natural kind of just flopping in the various s's for what we found, or for the sigmas. Okay, so this is going to look much like a z-score. So again, SA squared and SF squared going in a Z world, what would be, sigma A and sigma F. Okay, so there it is. That's the T. That's the T calculation. Okay, and again, we'll have a degrees of freedom calculation to do here in a second, and so we may want to do that and formulate our decision rule. We'll stick with the flow of what we did in the previous video, albeit a little out of order, but let's go ahead and calculate what this t distribution shows. This gives us 92.86 minus 92.44 over, and this bottom part being the, once we've taken the square root, we're really back to a standard deviation, and we can plug in 14.5 squared over 182 minus 12.4 squared over 176. And this should obviously be plus there. And so we're going to end up with a different, specifically here on the bottom. So the top is the same. We get 0.42. And the bottom is a little bit different than the previous example. And it's not going to be wildly different. It's going to look very familiar, but we are going to get a slightly different answer. And so this becomes 0.29 5. We rounded to 3 decimals last time. And so this is 0.295, and if let's jump back, and I think it was 0.297. Yeah, you can see it down there circled. So very close, very similar, right? And we haven't changed a lot. In this example, what did we do? We plugged our pooled variance in here, which was where did we have that? Let's jump back another sheet. We used the pooled variance, which is 178.82, but remember that's the equivalent of SP, the pooled standard deviation, of being 13.37. So basically we plugged 13.37 into this type of an equation, right? So we used 13.37 in both sides. Now in our unpooled version that we've just done, I'm going to flip back to what we've just been working on. We didn't pool it, and so instead of using the 13.37, we used 14.5 on one and 12.4 on the other. And so nothing drastically is changing, but the numbers are changing a little bit, and that leads us to a slightly different result. Now, in our purposes, that's not a big difference, and both of these are well away from any rejection region. But that's some of that is because we're using two standard deviations that are pretty close. 12.4 and 14.5 aren't wildly different, so that's not driving any huge result. We also are using sample sizes that are quite close. So when you tend to get sample sizes that are further apart, that can lead to larger differences. And then also, even though these are not a big change here, it could be that we'd be close to the level where we would decide to reject or not, right? So this could have, in a different scenario, flipped us over the edge of rejecting the null or not. Even this, 0.002. Okay, so the t's, but in general the t value is going to be typically pretty close. Because really all we're doing is either pooling it or not. So the other thing that we have to do here, though, is we need to figure out the degrees of freedom. Again, in our purpose here, we're not going to be able to claim that these two are different in their power. But for sake of working through all this, let's calculate the degrees of freedom. And this is where, so in this case, we haven't pooled. The math is easy, or easier, right? There's less, we didn't have to do the pooled calculation. So things were easy here, but we're stuck with a gross degrees of freedom. The degrees of freedom, I'm just going to switch to a new page just for this because it is gross. Let me bring with a little info here. Apparently I'm bringing with the 0.295. And let's write this down. So the degrees of freedom is the following equation. Again, if this gets too unlegible, it's obviously in your text. So for our purposes, that would be SA squared divided by NA plus, let's just write it like this, SF squared divided by NF, and all of that is going to be squared. And then that is all over SA squared divided by NA, this smaller part squared, and that's going to be divided by NA minus 1. Okay, and then the flip side, same type of thing here, and divided by NF minus 1. Okay, so this again is not going to be wildly different, or I don't anticipate it to be. Oftentimes it's within the ballpark of what we just calculated the last time. Let's refresh our memory. I'm going to have to jump back a little bit. We found 356. Now, this is again not going to be wildly different. However, you know, in other scenarios where we don't happen to be so far away from the rejection region, this can make a difference. So let's go ahead and we can plug these in. I'll change colors again so you can see it a little bit more. And this is going to be, let's see. So SA squared 14.5 squared divided by 182 plus 12.4 squared divided by 176, and we're going to square all of that. I wanted it in that bracket, I think. I got double brackets there. One of those is redundant. Okay. We can just pretend like we didn't make a mistake. Put some more brackets in. And then on the bottom, we have, again, 14.5 squared over 182. We're going to square that individually, divided by what equates to 181. And then 12.4. Put a square in there. That's right, 176. We'll square that whole thing and put that over 175. Okay, so you can verify this math, but that's going to give us what I believe is 4.116 roughly on the top and 0.0117 on the bottom, which gives us a degrees of freedom of 350.78, which we would round down. So we're going to round down to 350. Now, the reason we round down is that we want to take a little more conservative approach here. We don't want to overstate something. So we're going to do a lower degrees of freedom, which is going to lead to a larger t. Again, in this purpose, we're well beyond, we're approaching that infinity, not really, but we're well over the 200, and so the degrees of freedom of 350 is going to be approaching that 1.645 of a 10% z, even though we're in the t. Okay, so we have a large enough sample sizes here, and thus large degrees of freedom, that our t is forming what is almost a z distribution. Now, this is, what did we get last time? We got, compare this to 356, right? And so, not a large difference. Okay, so, actually, let me just, so we got 356 the last time. We also got 2.297, and in our case here, we got 0.295, I believe. Okay, so this was the t. And so nothing is wildly different, but again, this can be the determination, and also when we're in a if we didn't have such a large sample size, if we were dealing with sample sizes of 12 and 15 or something, this change of degrees of freedom can be enough to sway that critical cutoff point of the t-value quite a bit, and it can lead to either rejecting or failing to reject the null hypothesis. Now, just a little more discussion of what's actually happened here. We've changed from 356 down to 350, and what that has done is we've lowered our degrees of freedom, which means that we are using a slightly fatter distribution, right? Again, I'm going to kind of exaggerate this because we're way up in the 350s, so it's not that that much different. But we're using a fatter distribution in the 350 version, in this version where we're not pooling. And now, why does that make sense? What we're saying is that we don't have this underlying standard deviation, right? In the red case here, on the right, in our pooled version, this is the pooled. In the pooled version, we had this assumption that the standard deviations were the same, and so when we looked at the S's, we had two guesses for that standard deviation, and so we feel much more confident about what the standard deviation was. We had two reasonable guesses, or two unbiased guesses, and so we feel pretty good that standard deviation is close to whatever it was, 13.37. Whereas here in our unpooled version, we don't have that added level of assurance. So we're sticking with a little more uncertainty there, right? And it's a little confusing because, again, when degrees of freedom go down, that's a wider distribution with more uncertainty. So we're a little more uncertain about things in this unpooled 350 case than we are in the pooled 356. Okay, and so that's the process of degrees of freedom, of why we're doing that. We're trying to add in a little extra uncertainty along the way. So again, nothing wildly changes in our answers, and often doesn't, although again, I keep stressing this, but when we're talking about distinctions as far as, is this in the rejection region, have we reached the critical value, is our p-value going to be below the threshold, these little alterations can be the determining factor between rejecting or not rejecting the null.